An RC high-pass filter is designed to allow high-frequency signals to pass through while attenuating low-frequency signals. In this configuration, a resistor and a capacitor are arranged so that at low frequencies, the capacitor behaves like an open circuit, blocking most of the signal. As the frequency increases, the capacitor's impedance decreases, allowing the high-frequency components to pass with minimal attenuation. This filter is especially useful in applications where it is necessary to eliminate low-frequency noise or DC offset from a signal. Here's a simple schematic representation of an RC high-pass filter. In this circuit, the capacitor is connected in series with the input voltage, and the resistor is connected from the node between the capacitor and resistor to ground. This configuration forms a voltage divider in which the capacitor's impedance decreases with increasing frequency, thereby allowing high frequencies to appear at the output. As with the low-pass filter in the previous lecture, I'm providing you here with the underlying mathematics that describe the behavior of the RC high-pass filter. If you are interested in these details, then continue to watch. Otherwise, you'll find the most important takeaway formula, which is a cutoff frequency, at the end of this lecture. The behavior of the RC high-pass filter is described by its transfer function. The transfer function for an RC high-pass filter is shown here. To analyze the filter's response to sinusoidal inputs, we substitute S with omega, where omega is the angular frequency in radians per second. Now remember from the previous lecture that S is the complex frequency used in the Laplace transform. This substitution gives us this formula for the transfer frequency. The magnitude of the transfer function, which indicates the filter's frequency response, is this. At low frequencies, where omega times RC is much smaller than 1, the magnitude approaches 0. That means that the output is greatly attenuated. And conversely, at high frequencies, where omega times RC is much greater than 1, the magnitude approaches 1, and that allows the high frequency signals to pass through. The cutoff frequency, which marks the transition between these two regions, is defined by this formula. So Fc, meaning the frequency cutoff, equals to 1 divided by 2 times pi times Rc. This mathematical framework is derived from the voltage division principle, which takes into account the frequency-dependent impedance of the capacitor, expressed as 1 divided by J times omega C. This Python script demonstrates how to plot the frequency response of an RC high-pass filter. The plot shows the magnitude of the output signal in decibels as a function of frequency. When you execute this code, you'll see the plot that illustrates how the filter attenuates low frequencies while allowing high frequencies to pass, with the transition occurring around the cutoff frequency. The red vertical lines marks the cutoff frequency, which is also calculated by the script. Okay, let's have a look at the key takeaways from this lecture. The RC high-pass filter uses a capacitor in series with the input and a resistor to ground to block low-frequency signals and pass high-frequency signals. Here is the transfer function, which shows that the filter's behavior is frequency dependent. And here is the magnitude of the transfer function, which confirms that the output is nearly 0 at low frequencies and approaches unity at high frequencies, which means that the input is roughly equal to the output. The cutoff frequency is given by this formula here, which serves as the boundary between the stop band and the pass band.